Hi everyone, and thank you all so much for joining. Today, our speaker is Rebecca from SLAC. She is a senior graduate student who will be defending her thesis actually in a few months. And today, she's going to be presenting on observing the influence of atomic and nanoscale structure on the DC conductivity of warm, dense matter. And I want to encourage you, if you guys have any questions, please, you can ask them at the end or ask during the talk, but Rebecca does a wonderful job of explaining. So please ask. It's a wonderful time to learn. So with that, I will head it over to Rebecca.
Thank you. So as Kavita said, I will be talking about DC conductivities that are performed in the warm dense matter regime. I'm currently on the SLAC HEDS, and this is part of what I'll be defending in some months when I present the work of my PhD. So to start with, I'm gonna do a brief introduction of what is the warm dense matter regime. I don't know what to have everyone to introduce everyone to the topic, though I know many people have already seen this in the past. Now, to start with, talking about the warm dense matter regime, we are talking about a state that it's found all over our universe. It is a state that it's relevant also in many fields. And for example, in planetary science, you care about the transport or you care about the conductivity, which will be the topic of this presentation, in order to do better modeling of planets such as Jupiter or brown dwarfs, where warm dense matter it's really present. Also, going into a completely different field, we care about warm dense matter in inertial confinement fusion. So in order to be able to model better the trajectory from the cold fuel into the plasma, we need to understand the warm dense matter regime, and we need to be able to understand the transport in order to create all of these models that are then used on NIF or other places to understand what is going on the trajectory. Now, finally, we can also care about the warm dense matter regime if we are trying to understand instabilities. And this is a little bit connected into fusion in the sense of once you understand better the transport, so in this case, by understanding the conductivity, we understand some of the transport of the electrons. We can then figure out how this will be affecting how the instabilities will form in the system that we are analyzing. Therefore, in many different fields, we do care about warm dense matter. So, however, it is complicated. It is complicated to do modeling and to analyze all of these different problems that I have shown you, because warm dense matter has high temperature and high density. So going back into what is actually warm dense matter regime is a state that it's in between a plasma and a solid. So now if I were to have to define warm dense matter to you in terms of temperature and density, I will say that the warm dense matter regime, it's around 0.1 to 100 electron volts, where each electron volt, it's around 11,600 Kelvin, and also it's around 1 to 10 times the solid density. If you see this figure that I have on the left, you can see where the plasma regime is located in the top and where the solid region is located, and how the warm dense matter regime it's in the middle. And as I mentioned in the past, you can see how it's relevant for planets such as Jupiter or brown dwarfs, where you have a lot of material that is in the warm dense matter regime. Now, this will be a rough approximation because the warm dense matter regime is actually defined not as a range of temperature and densities, but about it's defined with two characteristics or two physical characteristics, which are non-negligible Coulomb coupling and non-trivial degeneracy. And by having these two, you end up having a state that it's really complicated to model. The reasoning being that normally on a plasma or on a solid, you have assumptions such as the system is cold enough, the coupling is relevant, or the coupling is not relevant on a plasma anymore. And you can neglect some of these contributions into your model. However, in this regime, nothing gets negligible, and you have to take everything into account, which complicates modeling a lot. So now, what actually happens when we say that we have something that it's really complicated to model? Well, here you can see some predictions that we have for the transport properties of the warm dense matter. In a specific, again, in this presentation, we will be talking about conductivity. So here you have some predictions of the conductivity and how it evolves when it's changing from the condensed matter into the plasma physics. And you can see that for a condensed matter system, if we were to predict the conductivity, we will be expecting that the conductivity decreases as you increase the temperature. When you go to a plasma, however, you will be increasing the conductivity as you increase the temperature. And in this region, in the warm dense matter regime, there will be an inflection point. When you try to model this inflection point and predict it using different type of theories, these theories break down, and we have what you see on the following figure, where we have several types of predictions, and these predictions do not agree. And this is the current state of the art of what we have for the modeling of the warm dense matter regime. Now, there are equations and there are predictions that we expect will be still useful in the warm dense matter regime. However, in order to understand it better, we need to have experimental measurements to benchmark these theoretical models that are actively being developed. And this is how we actually enter into the scene. So what we mainly doing here is we are doing experimental measurements that will be used to be compared to the models that I showed previously, or let me go back to the previous slide. We'll be giving experimental results that can be used to compare and to know which models are better or not, and which assumptions are correct or not. So now, I mentioned before that modeling the warm dense matter regime is hard, but also at the same time, doing experiments in the warm dense matter regime, it's equally as hard. The reasoning being, even if warm dense matter regime is really predominant throughout the universe, right? If we were to go to Jupiter or if we were to go to a brown dwarf, we'll encounter warm dense matter regime. Here in our atmosphere, having this state is really hard to achieve. So the way in which we do this on the lab is we have a really short pulse laser. So we grab a nanosecond or a femtosecond, in our case, laser pulse, and we have an initial solid state of matter. So we have a thin film in our case. We put the laser into the thin film or the solid state, and it begins melting. It briefly goes into the warm dense matter regime and finally converts to the plasma, expands, and so forth. So now, in our case, we care about the warm dense matter regime, and this transient state just lasts on the order of the picoseconds. So we need to have something that is fast enough for us to be able to characterize this state. Now, what do we actually do to achieve this challenge, or to succeed in this challenge? We do something that is called ultra-fast terahertz. We use something that is called ultra-fast terahertz radiation, which is a type of wave that is in between a microwave and an infrared. And there's two reasons why we use this type of radiation. So the first one is that the terahertz has a short pulse length. So as you can see from this picture, the pulse length that we have on the terahertz is on the order of 1 picosecond. And as I mentioned on the past, when you have warm dense matter created, it lasts on the order of picoseconds. So it is short enough for you to be able to measure and characterize the sample. But also, really importantly, at the same time, we have to remember that we are measuring conductivity. And the terahertz, fortunately, has a field that it's slow compared to the ion and electron motion. And how does this actually look when you are having something that is slow versus something that is fast? You will see in this figure that we have measurements of conductivity for a metal, in this case, aluminum, that are made using different types of waves. So if you use longer time waves, from radio to terahertz, you'll have a stable measurement. However, when you start going to shorter timescale waves, such as the infrared, you're going to start seeing other physical effects that are introduced by the wave. So you're going to have measurements that are not as stable, and this is not what we want. Therefore, we concentrate into using this terahertz radiation to make measurements of the conductivity of the sample. And when we're actually taking measurements, this is how the data looks. So in here, you can see the raw data and how we observe things on the lab. So terahertz is not a wave that you can easily observe with sensors. So we need to use this technique that is called electro-optic sampling. And the main thing that you need to remember about electro-optic sampling is that you will create some sort of birefringence or some sort of signal that comes from the polarization, and you will change this change of polarization, and that will be the signal that you will be measuring. And the more you change something, it means the more terahertz that are going into this system, or that are being transmitted in our case. So in here on the top, you can see the two polarizations. So we're using a Wollaston prism, and we are dividing the signal into positive and negative polarization when there's terahertz. And you can see the changes in these vertical lines. So because there's terahertz present in this part, you can see that some of the light starts going more towards one side and stops going into the other one. So this is what we see as a signal. So now, in order to quantify this, we want to clean this matrix that has information about the state of the mirror that we are using in this case. So what we do is we divide this matrix over a matrix where there's no terahertz present as a sort of reference. And the two of these, this positive polarization or this positive matrix over this matrix, will give us a signal or a intensity change that it's really similar to what you're seeing in this picture, in this specific matrix from here. So now you can do the same with the negative polarization, and you will end up with this matrix in this other way, which can average into these intensities that you're seeing on the bottom. Now, finally, we have a positive and a negative polarization change in intensity. So what we want to do in order to quantify a signal is we just add the two of them, because they should be encoding the same information. So this signal that you're seeing in this case is exactly the same as this signal that you're seeing in this additional case, which is represented on the most right matrix. And now here, once we have a signal that changes with time, we can simply change this signal directly into an electric field. And we do this because of the electro-optic technique that we are using. We have a really direct way to convert that has been previously defined in the literature, and has been used in many other applications. So once you convert into the electric field, we can convert into the waveform, and we do care about converting into the waveform. So we are actually able to give you a DC conductivity. So the DC conductivity, it's equal to the zero frequency conductivity. So we want to be looking at everything in the waveform domain. Now, going forward, we just saw how we start with a raw measurement of the transmission of the terahertz, and we obtain an electric field. And now that we obtain an electric field, we could technically get a transmission really easily by just measuring what is the signal through air versus measuring what is the signal through a sample. The air being the reference, and the signal and the sample being the electric field that you will be using to obtain the transmission. And we can simply obtain a conductivity such as the one that you are seeing on the right-hand side, a transmission such as the one that you can see on the right-hand side figure for copper samples at different energy densities and at different times. And I will expand more about this in the future. So once you have obtained the transmission, because we are using a thin conductive film, we can use this equation called the Tinkham formula, which directly converts the transmission into a conductivity. And we can observe that our measurements are really stable in the low frequency domains, which is relevant to the DC conductivity. And this is mainly how we obtain the conductivity measurements for our samples. So now going forward, as I mentioned in the past, we need a reference. So how our experiments look are it's represented by the following schematics. So you can see we have an array of holes where each hole will be an individual sample. So if we were to focus the terahertz through this hole, we'll see the transmission by seeing how much terahertz actually goes through the detection. And it'll be measured as a signal, as I explained in the past. So now let's assume this is how it looks through air. I could potentially put a thin copper film and see how much terahertz gets transmitted through the film. So now here you can see how the signal will vary for these two and how it will look compared to one another. We obviously had to increase the signal for the cold system because the signal is really small compared to the air or to the reference. And finally, we could also focus on the same spot, an intense optical pump. And this pump, what it will be doing is it will be exciting your film. So it will increase the temperature and it will take this film into the warm dense matter regime. So now in this case, you can see how the signal will look for a sample that is excited up to 12,000 Kelvin. And you can see that there are some differences in all of them, and we can capture how much the terahertz change. And this terahertz change can then, as I mentioned in the past, be translated into a transmission that will then be translated into a conductivity. So now, as you can see from here, for a cold sample versus for a hot sample, we can observe a really big change in conductivity. And this is mainly what the technique that we are doing is measuring. Now, before I start analyzing the results, there is something that I really need to focus or explain before we continue going forward. As I mentioned, we say that we are observing structural effects in the conductivity on the warm dense matter regime. So in order to explain everything in a way that makes sense for people that are used to condensed matter, when we are taking measurements of a thin film, we end up finding that our conductivity is way lower than the conductivity that we will expect for the literature value. And what do I mean by this? If we measure the conductivity for our films in cold, in ambient temperature, using both the terahertz and also an independent 4-point probe system, that it's a different way to measure conductivity, we will see that our conductivity is equal to 2.9 Siemens, 2.9 into 7 Siemens per meter, which is about half what it's predicted for bulk copper conductivity. And why does this happen? Well, the main reason is because in really thin films, when you're going to a nanometer scale film, your system will actually be composed of many little crystals that are attached one to another one. You won't have a main bulk system as if you were to have thrown just melted copper into a bucket and just let it crystallize by itself. So in this case, you can see here a TEM image of our copper films, and you can see these small grains that are around the size of 10 nanometers. So now in condensed matter, we are aware that these nanograins, decrease the conductivity because you normally have electrons that are traveling through the film, and you have normally a mean free path depending on the material that you have. In here, for copper, you have a mean free path that it's around 40 nanometers. Therefore, if you have a grain that is smaller than these 40 nanometers, what's going to happen is the electron is going to try to travel forward. It's going to encounter the edge of the grain, and it's going to scatter around. And this is scattering, so these collisions that you will have will decrease the conductivity because the electrons cannot travel as freely. Now, this might be a little bit confusing for people about how this is relevant for a plasma or for a system that it's in between a plasma. However, we need to know, or it needs to be explained, that this is something that it's really well known for condensed matter. And we also know that the lattice in the warm dense matter regime stays present for some time. So we know lattice in the condensed matter affects the conductivity. We know there's lattice on the warm dense matter regime, but up to now, nobody has ever accounted for effects of the lattice in the conductivity in the warm dense matter regime. So our measurements are able to see these effects. And this will be important going forward into understanding how we are able to predict that structure has some effect in the conductivity. Now, let's go ahead and talk about the results that we obtained for our measurements. Now, to start with, once we can obtain the conductivity for the system, we can start doing some time result measurements where we vary the fluence. So in this case, by varying the fluence and the time, we are actually seeing what is the evolution and how there's a variation of conductivity with time and with energy density. So in here, you can see some figures in which we can see how the time evolution of the conductivity goes for different amount of samples. And in the background, you can see what is the predicted state of the system. So if I said it's solid like warm dense matter or its coexistence, we are meaning that there's still some of this lattice present. So some of the lattice that I mentioned to you that it's well known in condensed matter to affect the system. So now in here, before doing any prediction of how important one versus the lattice versus the interaction between electron and ions are, we can start by just observing that there seems to be a connection between the conductivity trend and what is the phase of the system. So in this case, you can see that we start with a cold system that has a high conductivity. As soon as you excite it, the conductivity drops really quickly. And then once you are in the solid region, so in this region where you'll still have a lattice present, you seem to have a stable conductivity for all cases. So a conductivity that doesn't seem to change a lot. And finally, the system will start melting, the lattice will start decreasing, you will have some expansion, and your conductivity will start continuously dropping. So we observe from here, without doing any sort of analysis, that there is this trend between the phase of the system and also like the conductivity. Now, this could be due to structural effects or temperature. So what we're going to do next is we're going to try to separate all of the physical effects from each other. And in order to do this, we first need to understand how the temperature evolves. In order to do this, we don't have direct measurements, but we can do this thing called the two-temperature model, in which we use this model that you're seeing on the right, and we assume that we have some sort of energy density. We put a range of times, and we can observe how the temperature for the ions and electrons is changing for the system at a given time. Now, we also need to analyze how the system ionizes, how many free electrons you have. So we'll also be doing a density of state calculations, in which basically you're trying to analyze the change of electrons in the bands or the densities. So also, in order to do all of the predictions that I did in the past, where I said the system is melted versus the system is still with lattice, it's still solid like warm dense matter, we use previous measurements on the UED. However, I won't be discussing this a lot. I will just mention that we use these measurements in order to predict what the state of the system is. Now, going forward, I mentioned to you that we want to divide, or we want to understand what is affecting the conductivity. And the easiest way in which we can do this is we can separate the conductivity, or we can convert the conductivity into scattering. So we can simply do this by using the Drude formula that directly matches conductivity into the total scattering. And the scattering is relevant because you can separate the scattering into what part of the scattering is coming from the electron-ion collision, what part is coming from the electron-electron collision, and what part is coming out of the grain boundary scattering that I talked to you in the past. So basically, by using this technique, we can divide the conductivity and see the hierarchy of all of these different elements that are changing the conductivity on the system. Now, I mentioned here that it's really easily to change from the measured conductivities that we have into a scattering. However, in order to analyze or to see how each of these individual scattering systems is affecting, we need to start doing assumptions. And some of the assumptions that we can do that helps us, like the assumption that we can do that helps us solve for this system is we do the assumption that the electron ion scattering is dependent on ion temperature and is just a linear function. So in here, you can see how for total scattering, we obtain the measurements from the terahertz. And once we assume that the electron ion scattering follows what is predicted on the literature and also at the same time just increases with time, we'll have a line like the one you see in here. And the reason why it's not a linear line is because we have some samples where the thickness varies a little bit, but it's following a linear trend mostly in what you're seeing here. Now, once we are able to obtain the electron ion scattering, we know that we can obtain the grain boundary scattering for the system because this is mostly the other scattering that you have that is relevant on the ambient film. And it will be the difference between the scattering that we have and the scattering that is predicted for the literature. And finally, because the total scattering is a sum of the three types of scatterings, we can obtain really simply the electron-electron scattering by just subtracting the electron ion and the grain boundary scattering from the total scattering. And now finally, as I mentioned, we did some assumptions. So we could start building a model in which we can, or a semi-empirical model in which we feed our values, and then we can predict what type of a scattering we have, not only for what we have measured, but in general for any type of copper film or copper sample that we can expect in the warm-dense matter regime. And these equations that you're seeing here are the equations that we use to predict the system. So now, in order to see how our predictions work, we can observe here a plot where I have the different type of scatterings that can be predicted for copper. So I have the total scattering, electron-electron, and the electron ion. And in green, I'm plotting the experimental measurements of the terahertz. And I am plotting some solid lines with a 10% error bar, where I'm showing how the fits of these equations that I just mentioned compared to the measurements that we have. And you can see that there is a good agreement in our system. Now, I also want to mention here that, of course, this model we are doing to try to predict copper, not only our experiments. So in here, I added some data, which you can see as pink triangles in the bottom plot, where I'm comparing our experimental measurements with our model. And in addition, I'm adding independent measurements that were done with a different technique called ultra-fast electron diffraction that I mentioned in the past. And these are two different measurements, and we do follow a trend that is really similar. And while there are some values that don't match really well, we seem to be going through the same trend and matching in some of them. So now that we have created a model that can predict our scatterings, we can revert back and obtain the total scattering from the sum of our electron ion, electron-electron, and grain boundary scattering, and obtain a model for the conductivity of the system. So now in here, in this plot, what you can see again is our measurement of conductivity plotted versus electron and ion temperature. We are also adding measurements of a 4-point probe, where we are seeing just a comparison or a validation of our measurements. And I'm also adding measurements of the literature, so you can see how much our values differ from what is expected on the literature for bulk copper. And now what you can see on the solid lines, it's the model that we have created for the scattering converted into conductivity. And you can observe that especially when the system is cold, the model matches really well to what we are expecting for conductivity, which shows that in order to understand the system, we need to account for grain boundary scattering from the beginning, right? Where we are seeing that in our cold sample, there's such a big difference with what is expected with the literature. And we knew this from the past. We knew that grain boundary scattering is relevant. However, we also observed that even as we are increasing the temperature, as we are advancing in temperature, this grain boundary scattering is relevant for the system. So you might be wondering up to which point the grain boundary scattering is relevant, at which point the temperatures start dominating the effect. And the way in which we can analyze this is we can simply revert and go back to our time result measurements that I show you from the beginning. And in the background, I can say where my system is expected to have temperatures that are smaller than the melting temperatures, or I can go even further on and measure and explain where our system is expected to start melting. And this start of the melting is defined by a percentage, or which percentage of lattice, which is the FCC, is still present on the system. Now, I hope that you can observe in here that for a system where we are not expecting to melt, so before the 98% FCC is achieved, you will be clearly following the prediction that includes the grain boundary scattering. However, as soon as the system approaches this melting and starts melting, even with a really small percentage, you change and then you start behaving as you would have predicted for a bulk copper. So you suddenly go from a system that just behaves and it's bounded by the grain boundary scattering to a system that behaves as the grain boundary scattering never mattered. So this is really important. This is really cool and really important. And it shows that structural effects, even when they haven't been accounted in the past, are relevant in the warm dense matter regime and need to be accounted for up to the lattice on the onset of lattice. Sorry, I'm seeing it's hard for me to see if there's questions. So feel free to interrupt me if you have. And
I'll
I'm
interrupt
close.
for this question that was
Yeah,
posted. So there was a question posted. Are you
yeah.
in a regime where you go from solid directly into a plasma, or do you always go through a melt?
So the warm dense matter regime is defined as a regime in which you are already from a solid and you haven't yet arrived to a plasma. So it's the transition between these periods. So what ends up happening is that you excite your electrons. So your electrons go at a super high temperature. So you have an electron that it's around, you can say up to 10,000 Kelvin, but you have a lattice that it's still cold. So you could have a 10,000 Kelvin electron that it's still on an ion temperature of 300 Kelvin. So it is a
Could I just follow
really
up with a
Mhm.
question on that? Thank you. So when you say melt, that's talking about ion motion, really.
When I say melt, what I refer about, it's mainly talking about lattice. And that's a good thing that you're bringing this up. I should have clarified this. So in this regime, we say that we are on the warm dense matter regime because we have really high electron temperatures. However, the way in which I'm defining what I call solid-like warm dense matter regime, coexistence, and so forth is defined based on the lattice. Therefore, if you have a lattice that it's cold and that you still have lattice present, that's when I'm saying I have like a solid like. But then it starts melting and you have a liquid like lattice. And it's not yet a plasma. It's just like a liquid with a really high temperature. So again, the complicated part about this state is that you are not in between them. There's not a significant ionization as you will expect with plasma or anything like that. It's just a regime that it's still really dense, but it's also still really hot at the same time.
Thank you. That's perfect.
Yeah. So going forward, as I said, we can observe this really cool trend in which in this regime, the grain boundary scattering, so the structural effects are important, which means that we need to change the current models that are being created, and they need to account for the grain boundary scattering up to the onset of the lattice, and then you can predict what is the next system, or if electron ion scattering or electron scattering will be more relevant for your system conductivity. So now let's understand what are the implications of what we are meaning and why is this jump happening. And we have a hypothesis of why this is happening. So now let's go again and look at these measurements where I haven't started melting. So as I mentioned, in here, we are expecting that we have really high energy for the electrons, but the lattice will still be cold. So what's going to end up happening is what you're seeing on this figure from here. You have a lattice that it's mainly there. It hasn't been affected. For the lattice, you are still at cold temperature. And you have electrons that are really excited from the laser interaction. The electrons will be traveling really fast, and then they'll arrive to this border between the grains where the lattice changes, and they'll start scattering. And all of this scattering will decrease your conductivity. And this is still true before you start melting, even when the temperature of the electrons has changed a lot and you're technically on the warm dense matter regime. However, going forward, why are we suddenly changing and the system is behaving as if the grain boundary scattering or the structural effects never matter? The reasoning is simple. When we are talking about grains and when we are looking into grain melting, what ends up happening is that the grains start melting from the outside to the inside. And this boundary, this hard and rigid boundary that you used to encounter in the past, now starts being a soft, a soft transition into these different type of lattices. So what ends up happening is the electrons that are going really fast and we're just bouncing around now encounter this slight change that doesn't necessarily decrease their movement by a lot. Therefore, what ends up happening is that the conductivity doesn't decrease because of this transition, and then you end up having a system that behaves like you will predict for a bulk system. And that is mainly the lesson that we have learned here. So now I'm going to go forward and I'm going to talk about the summary of what we have seen here. So this technique, the terahertz single shot spectroscopy, is a relatively new technique. We have done analysis on other metals, and now by analyzing copper, we are trying to show and demonstrate the capability of us to make measurements of copper and to have really small error. So the reasoning why we can see all of these changes is because we have this small error and we are able to see what's going on for solid, for liquid, for differences in 1 picosecond. Now, I also hope that you have learned that the conductivity of warm dense matter regime also needs to care about the structure and not only the atomistic effects, such as the temperature and the electron and ion temperature and the density. You also need to care about the structure until the melting of the lattice. And finally, I hope that you have seen that we have created a model that is able to predict the behavior for conductivity, both for something that is solid and something that it's beginning to melt in the warm dense matter regime and has melted in the warm dense matter regime. Now, what are the future steps of what we want to continue doing with this research? We want to, first of all, a really simple way to go about this is we want to expand these conductivity measurements beyond copper. So we could potentially analyze more complex materials. We could go, there's plenty of things in condensed matter that are not accounted for in the warm dense matter regime. We could go and take potential measurements into other metals and analyze if these condensed matter theories are also applicable at the beginning in the warm dense matter regime and when it stops affecting the system. We could also potentially go into amorphous materials. We could analyze carbon and we could see how the conductivity changes, which might end up being relevant in ICF. As we know, we use high density carbon for the fuel pellets. Now, potentially, as I mentioned in the past, one limitation that we have is that the temperature and density measurements are done with modeling, or not measurements. The temperature and density are calculated throughout models, but we could potentially improve this by doing direct measurements using XRD and XRTS. And this is something that my mentor, Ben, has been looking at, and he has already achieved and completed a beam time at MEC in SLAC in order to do this type of measurements. Now, in addition, we could do study the pressure dependence. So in these measurements that I have shown you in here, we excited the system with a laser, but we didn't change the pressure. So we could simply go ahead and ablate the system in order to also create a change in pressure and a change in temperature. And we have done actually this on the past. And we have completed a beam time at JLF, and we are in the process of writing some more about this. And finally, as a graduating PhD, what are my future steps? It's I really need to go forward and continue working. I'm doing a publication regarding all of the results that you're seeing here. So I'm hoping we get to publish it really soon and you can read it more to your pleasure. So these are what we are working on. Now, before I finish, I really need to acknowledge that this work has only been possible due to the fact that I have a great team and they have supported me a lot throughout my PhD and throughout this project. And I want to acknowledge every one of them and just show their pictures. And obviously, this has also been achieved because of money. So I need to put our funders there. And that will be all. Thank you very much.
Thank you, Rebecca. And if the audience would mind joining me in congratulating her and thanking her for an excellent talk. So with that, let's take questions from the audience. You're welcome to unmute yourself and ask, or drop them in the chat, or you can drop them to me privately, whatever you guys would like. So I'll go first. I have several questions. The first one I'll ask is a little bit of like, hopefully maybe an easier one, but can you go a little bit into kind of your experimental setup? I mean, you showed like amazing experimental results. Like, what was your terahertz source, for example? Could you
Yeah,
just talk a little bit about that?
I do have a slide here that shows all of the experimental setup. So the way in which we obtain terahertz is we start from a tabletop laser. We divide it into what I will describe as three different paths, but you can describe it as two different paths if you wish. So you put it through a BNA crystal, and this BNA crystal does what's called optical rectification. So it gets excited and it releases terahertz from the 800 nanometer initial beam that we are inputting into it. So that's our source.
Gotcha. Yeah, because like you said, the terahertz sensors you mentioned are very like, I mean, you had to get creative with measuring that. So I was also curious how you did that. So thank you for
Yeah,
explaining that.
so the way it's a bit more complicated to explain how is that we are measuring, but it's also shown in this schematic. So the measurement also has to be done through a nonlinear optic, which in this case we use zinc telluride. And basically what we do is, as you notice, there's some sort of time attached into the measurements that we have. And that is due to the fact that when we are doing this type of a spectroscopy, we are doing a time domain spectroscopy. So we put a terahertz into the nonlinear crystal, and then we etch the time by using an echelon. So that gives us a bunch of beamlets. I don't know if you're like if you have worked a lot with echelons, but basically it divides a main beam into a bunch of beamlets, so it encodes a time on it. You pass it into the crystal that as soon as it reacts to terahertz, it becomes birefringent. So then when the beamlets go through it, they see on a really brief period of time how the terahertz how the nonlinear effects happen. So that's why we can see in this figure, let me show you really quickly. So in this figure, that is why we have some time encoding here, because the echelon steps are in this direction. And you can actually see the small lines in here. These are the steps. And you can see here how the terahertz pulse is going through. And in this time, it's just becoming more birefringent towards one side. So that is how we end up doing the measurements. That's the specific setup that we do.
Thank you. There are questions from the audience.
I had another question, Rebecca. Nobody else, I don't want to steal the time. But the graph or the figure you showed where you had the grains melting or becoming more disordered at the boundaries first was quite interesting.
This
Have
one?
you?
Oh,
Yes.
I put the wrong one. This one, yeah.
Yeah. Have you considered trying to image these grains as they're undergoing this transition with something like Bragg coherent diffractive imaging or dark field microscopy?
I haven't. I think that's a really interesting suggestion. I think it's well known that the grains melt from outside to inside, but it will be really cool to be able to measure these on the warm dense matter regime and to rectify it. And I think that is what's important about this type of research that we are doing, right? It's opening questions about what is actually happening on the system. And perhaps at some point, these type of measurements should be done and accounted for, and that's how you'll know when you have to account for condensed matter versus non-condensed matter for the warm dense matter regime.
Yeah,
I haven't thought about it, and unfortunately my time is running short in the sense of I'm graduating, so I think my mentor is present here. He might get more interested into this, perhaps us doing a future collaboration depending on what I end up doing, but it's really what you're asking. It's really interesting. I will be interested to see what happens and how it actually starts melting. The way in which we are doing the predictions is we are doing a two-temperature model coupled with molecular dynamics. So as I mentioned, one of the limitations that we have is that many of the things that we are using to do these predictions are models. And this doesn't necessarily mean that this is a bad way to do the predictions, but we could improve potentially by doing all of these analysis. And the X-ray diffraction that we try to do for the terahertz, while it doesn't necessarily image the grain and we can see how this is transitioning, we can observe the peaks and how the peaks are broadening once the system starts melting.
Very cool.
Mm-hmm.
Thank you.
Well, I have another question. So,
Yeah.
this is related to like the copper thin films. Like, how do you guys actually, produce these thin films? And it's a multi-part question. So let me ask that first part first.
So I guess I'm going to disappoint you up to a point because I did get into nanofabrication. They do have a wonderful laboratory here at Stanford with great people. But I ended up spending a lot of time there, and we ended up finding that, for both for in order to machine the thin films and to create them through the nanofabrication and everything, I needed to do films that were really robust in the sense of there was a lot of variation. It was hard to do the measurements really precisely. I was just getting trained on it. So we actually ended up deciding for another path, which was getting the films done outside of our house. I don't know if that's how you say it. So we get them made in the UK. And
Okay.
they have some way to have we have noticed that the measurements tend to be more clean and they tend to be more, the holes don't vary a lot in sizing. The thing though is that from what I believe, they are doing some sort of deposition. So they might be doing sputtering or CVD. So you start growing, you have basically how these techniques end up working is you have some sort of system that excites your atoms. You might have some sort of solid sample that you excite with an ion beam, then some atoms of like this solid, so in this case copper, start flying around a system that is just mainly composed out of argon. So then this copper goes and deposits into where you have your substrate that's holding your film. So now in our case, basically what the people do is that they do this sort of technique, but first they start with a silicon wafer. On top of the silicon wafer, they put some silicon nitrate. They put a thin film of silicon nitrate, which is transparent for terahertz. And then on top of it, they put copper or the material that we're asking for. And then they have some sort of milling technique that then they use to mill out the silicon substrate and to do the holes that way.
Gotcha. And like you said, making these thin films are not trivial at all. It's like you said, it's a very complex process.
Yeah.
But do you think like the thin film quality is going to affect some of these results? Like let's say you were to make use like atomic layer deposition and make like a really, really nice copper thin film. How is that, do you think, going to affect like the grain boundary? Um,
So I guess we had some problems regarding the quality. So not going into really a specific deposition or something, there was a time where the conductivity measurements were not making a lot of sense. So I had to learn how to go and grab these sample films and measure what the thickness was. So in this sense, what ended up happening is that because of we had some sort of error that can be like 10 nanometers will give us a completely different result.
Yeah.
So in this case, this was a problem for us for some time because as we were not aware of this type of change, and as you notice, our conductivity is obtained by doing some sort of division versus the thickness. Let me show you here the equation. This was giving us some trouble. So here,
Yeah.
for
Well,
the
your films
thickness
were
formula,
originally
we care about the
30 nanometers, so 10 nanometer deviation's a lot, like,
yeah,
too.
so in that case, because we are dividing over the thickness, that brought us a lot of problems.
Mhm.
However, when you are talking about the type of deposition, if you can do it really carefully or not, as long of course, if you have a lot of defects, right? If you think you have a copper sample, but you end up finding that 5% of the copper, it's like 5% dope somehow with carbon or with other material, that's going to bring us a lot of problems. But the main thing that we are trying to figure out here is that as long as you have some sort of density that you are expecting, right? As long as the is not pure like argon bubbles also in there, and you have copper, it doesn't matter what type of grain you have. You have the grain boundary scattering happening, and this is really easy to measure in the cold system. Therefore, it doesn't matter if somehow you're able to measure the conductivity and somehow your deposition is so good that you create like a single crystal measurement, you'll be able to see this and to know that the grain boundary scattering is negligible from the beginning. And also like if you have something that it's really bad and you have crystals that are 1 nanometer in size and you have so much, scattering going around, you also be able to measure these. And basically, by being able to measure these, you'll be able to predict how the system will evolve. So as long as you do this type of measurements and you're aware of the quality of your sample, you should be able to continue doing the predictions with no problem.
Yeah. No, that's great. And, like you said, like making a perfect thin film is going to be virtually impossible. I mean, it's going to take a lot of time. And if we're thinking about, the application of IFE, we're trying to mass produce these targets very, very
Yeah,
quickly. So the quality is not necessarily going to be perfect. And so it's important to understand what's going on in this regime as we're starting
yeah,
to implode these targets.
exactly. You said it perfectly.
Yeah. Thank you.